Hi everyone! In this video, we're going to learn about the first translation theorem that simplifies the process of finding the Laplace transform of certain functions. First, let's refresh the definition of the Laplace transform. Remember, it's an indefinite integral that we apply to the given function multiplied by the function e to the power negative st. And for example, if we decide to use this definition to evaluate the Laplace transform of the function t to the power 10 multiplied by e to the power 7t, then we have to repeatedly perform integration by parts. And that becomes a pretty time-consuming and tedious process. So the good news is that we're going to learn what's called the first translation theorem that will save us time when we try to evaluate functions of this form. Now, what form is that? Let me give you another example. Here's one more example of a function for which finding the Laplace transform using the first translation theorem becomes very easy. What do you think these two functions have in common? You probably noticed that both of them represented as a product of two functions, where one is e to some power, so e to the power 7t in the first one, and then e to the power negative 2t in the second one. Well, that's going to be the form. And I'm going to give you the formal definition of the first translation theorem in a minute. But for now, let's continue working with these examples because they're going to illustrate how this theorem works. So if I focus on the first one, then all I need to know to evaluate this Laplace transform using the first translation theorem is the Laplace transform of the function t to the power 10. And we already know that the Laplace transform of this function is 10 factorial over s to the power 11. And as a quick reminder, I just used the table of Laplace transforms to find that. So here's that function and the corresponding Laplace transform. So going back to our example, again, if I know what the Laplace transform of t to the power 10 is, the only thing I have to do to find the answer to this Laplace transform is to take this result and perform the horizontal translation of this function, or shift. You might remember from algebra then, whenever a function is translated or shifted horizontally to the right or to the left, a number is being added or subtracted right next to the argument or the variable of the input. In algebra, it's usually variable x. In our case, it's the variable s. And now the question is how far we translate or shift this function to obtain the final answer for this Laplace transform. Well, the power of e will tell us that. We just have to look at the coefficient of t, and that's the number we'll use. So look at the final answer. The result has the same form as the Laplace transform here, with the only difference that instead of s, we have s minus 7, which came from the power of e. And yes, the sign is opposite here, and it will always be. Let's try it with a second example. So to evaluate this Laplace transform, we only need to know the Laplace transform of cosine of 4t. And we already know what it is. It's s over s squared plus 16. Once again, I simply use the table of Laplace transforms. So here it is. And next, we're going to perform the horizontal translation or shift of this function, which means that right next to s will appear a number. What number is it going to be? Well, we have to look at the power of e. Well, it's negative 2t. We're going to use the number negative 2. So the answer will be s plus 2 over s plus 2 squared plus 16. Once again, the sign is always going to be opposite. So that is the idea of the first translation theorem, and now it makes sense where the name comes from. So let's look at the formal definition of that theorem. So it says that if a is any real number, and then what is a? Well, a is the coefficient of t in the power of e. Then the Laplace transform of the function that has the following structure, e to the power at times some other function, equals to the horizontal translation of the function f of s, which is in its turn the Laplace transform of this function f. After we already did those two examples, I think this formal definition of the first translation theorem should make sense. And what we'll do next, we're going to look at the inverse form of this theorem. In other words, what happens if we apply the inverse Laplace transform to both sides of this equation? So on the right-hand side, we have the inverse Laplace transform of this shifted function f. And on the left side, the inverse Laplace transform and Laplace transform basically cancel each other. So that's how we get the inverse form of the first translation theorem. And once again, it gives us the shortcut. If it happens that we need to find the inverse Laplace transform of a shifted function, all we need to know is the inverse Laplace transform of the original, not shifted function. And the result, f of t, will be over here. And the amount of the shift, I'm talking about a, will be put in the power of e. So it's going to be e to the power at. Let's try an example like that. So in this example, we need to find the inverse Laplace transform of the function 2s plus 5 over s squared plus 6s plus 34. And we're going to use the inverse form of the first translation theorem, for which we need to basically know which function is being translated. And it's not obvious at this point, right? Because in the translated form, there's always same number that's being added or subtracted right next to s. And we don't have it here yet. So the way we're going to start is by completing the square in the denominator. So to complete the square, I'm going to write s squared plus 6s. Then I have to think what number to add here that creates a perfect square trinomial. Remember, it's always half of the middle coefficient squared. So 6 divided by 2 squared, that's 3 squared, that's 9. I have to put 9 here, but then as I add this extra number, I'm going to subtract it, so that in fact I'm not really changing my original expression, and I still have plus 34. Now the first three terms create a perfect square trinomial that we can write in squared form. It's s plus 3 squared, and the remaining constants would give me positive 25, so plus 25. So this is what I have in the denominator right now. S plus 3 squared plus 25. And I'm starting to see the translated form, so now I have number that's added right next to s. And that should be same number that's added to every variable s in my function. So that means that it has to be same case in the numerator. So what I'm going to do, I'm going to write what I want to have. And that is s plus 3 in the numerator. And it's important to put 2 outside of the parentheses. And then I have plus 5. And now let's see how we have to fix this so overall my numerator is not really changed. So basically by putting plus 3 right next to s, I added another 6, because if I distribute 2, it's going to be plus 6. So I added extra 6 in the numerator. I have to subtract it so that overall my expression is the same. So I'm going to put minus 6 over here. So this is what I have. The inverse Laplace transform of 2 times s plus 3 minus 1 over s plus 3 squared plus 25. To continue with this inverse Laplace transform, I'm going to split this expression into 2 in this manner. And now we're ready to apply the inverse form of the first translation theorem, because now we can see how each function is a translated function. Every variable s has the same number being added right next to it. And according to this inverse form, the only thing we need to know is the inverse Laplace transform of the original not shifted function. In other words, what is the inverse Laplace transform of the function 2s over s squared plus 25? Now to see that, I'll just make a few small modifications. I'm going to put 2 outside of the inverse Laplace transform, and I'm going to write 25 as 5 squared, like that. And from the table of the Laplace transforms, I can see that this represents cosine function. So it's 2 cosine of 5t. And for the second inverse Laplace transform, again, if I rewrite this function as the original not translated or shifted function, it's going to be the inverse Laplace transform of 1 over s squared plus 5 squared. By looking at the table of the Laplace transforms, I can see that this is very close to the sine function. The only thing that I have to have a in the numerator. So my a is 5. So I'm going to write 5 in the numerator because, well, I want it there, but to make sure that nothing really has changed, I'll have to put 1 over 5 in the front to cancel that 5 that I wrote. So that's going to be equal to 1 over 5 sine of 5t. And now we're ready to write down the final answer to our original question. And once we find the inverse Laplace transform of a non-shifted function, we're going to put together the final answer using this form. Each result here will have to be multiplied by e to the power at, where a corresponds to the amount of shift. Remember, always use the opposite sign. In other words, the answer will be e to the power negative 3t, that came from here, times 2 cosine of 5t, so I better put 2 in the front, and then cosine of 5t minus, and then the second part of the answer is 1 over 5 e to the power, again, negative 3t, and then sine of 5t. So this is going to be the final answer. And once again, in this example, we use the inverse form of the first translation theorem.